All right, so this is Mark Nixon. Mark started his career as a systems engineer working on projects in oil and gas, chemicals, and pulp and paper. He moved from Canada to Austin in 1988, where he has held positions in both research and development. He was a lead architect for Delta V from 95 to 2005. In 2006, he took a very active role in the design and standardization of wireless hardware. He is involved in several standards groups, including ISA, IEC, Buildcom, IEEE, and Oasis. He is one of the cause editors of ISA 101. He currently leads the applied research group where he is pursuing his interest in control, analytics, wireless, mobile, and advanced graphics. He holds over 200 patents, authored over 100 papers, and has co-authored several books and book chapters on wireless, control, and control systems. He is an ISA fellow and in 2012 was inducted into the Automation Hall of Fame. In 2022, he receives a Faculty of Engineering Alumni Achievement Medal in the Professional Achievement category from the University of Waterloo. He received his bachelor's from the University of Waterloo in Canada.
All right, thank you so much. First of all, I apologize to everyone for being so late. I live quite a ways east and got caught in all the rain, and 1:30 was a parking lot and 35 is a parking lot. So it goes. Anyway, so 2 hours of driving later, I'm here. A little bit late, but let's go with the presentation. I appreciate everybody coming, listening, and seeing what we've been working on. I'm going to move right on up. The project here was done by a number of us. I'm not Shu, obviously. Shu was unable to make it here today. Noel was the backup. He also couldn't make it, so I was third in line. So here we go. So we're going to go through the flare gas recovery system and how we address this. This project has a little bit of background, which is interesting. It was initiated through the Center for Operator Performance, which is a group that I have been working with for over 10 years, and Ken Cahill and others are certainly well aware. The objective here, because of regulations and other internal requirements that some of the refining and chemical companies who are still part of the COP, was to provide the operators with a 15-minute early warning of impending flare. That was the objective. We were also given a fairly liberal objective in that it was okay to give an indication of the flare, even if it didn't happen, because the consequences of the flares were higher than having to deal with them more often. I know that's generally not what people want to hear on predictions, so that meant tightening it down a bit more. So this is a flare gas recovery system. Many of you do this stuff. I'm if this pointer works. Yeah. So anyway, obviously on the the flare gas coming in, we can recover the gas, we do, or we try and set it off to the furnaces and burn it, or use it, or compress it and do something else. One of the objectives with the refinery we work with here, from the top management, was to reduce the number of flares to 0 per year. So it's very, it gave us a lot to work with. So the first objective is avoid or reduce flares. Predict conditions that lead to flares and provide operators with an early indication. So the 3 things, and we looked at all of those. $18 units feed into the flare system that we looked at. We had quite a bit of data to work with. There was we used like 115 variables. I remember the project. All of that. The pressures, was, were largely the key thing that we used. There was, obviously it was raw data as a plant. We used 1 minute data. No need to go faster than that. You can even argue that's too fast when you're looking at the overall movement, but that was the level of detail that we worked with. And so that's what it looks like if you plotted, which is meaningless, of course. You can see the flares on the top illustrated. Of course, you wouldn't see it that way. You can see the spike in the data. So, you know, some temperatures as well, obviously. So looking at the data, what you can see here is there is some bumps in the data. This was here for 1 month of data that we used that they gave us for. And you can see this recurring bump every day. The natural variation in the heat is really what you're seeing there. You have a big sun out there and heat stuff up here. And so this particular refinery is on the coast here in Texas. So obviously it's going to see that. You can see that everything is scaled here 0 to 1 to make it easy to work with. This one here, sorry, on the first one, there are no flares. This one has a flare vent right there. And so obviously we want to predict that. You can see some variations leading up to that. So the question is, can we find that in the data and use it to predict it? So we used a number of methods to look at the data. We looked at the data in both time series and frequency domains. And went with that. We used fast Fourier transforms. We used some wavelet stuff. Using this technique on its own, you can see here we could only predict 5 of 14. That's better, but that's not good enough. So what else can we do? So we went and looked at a number of other techniques, both hierarchy as well as hybrid style. And so here, looking at it, we looked, first of all, the first runs were done just looking at the flare gas recovery system, all the variables. So that's not helping us. So then what we said is let's look at each of the units separately. So we have 18 of these now feeding in. And we can combine the signals to an overall index. That avoids this swapping of one thing for another, which was very, very useful. Then we had some hybrid technique here, where we use frequency domain as well as time domain data. These were the techniques that we used. Obviously, PCA is kind of a bread and butter technique for machine learning. It's been used everywhere. A lot of work, good work was done by the University of McMaster and other places, very successful. We looked at a dynamic PCA, which accounts for time lags in the data. Refineries and chemical plants can have very long time. And so adjusting that data can really help with the analysis. And that's one of the things that we did. We use wavelets. Not sure the wavelets help us that much. We got really cool visualizations on the wavelet data. That's looks good when you're presenting. I didn't do that here. You guys want to see results. We looked at slow feature analysis because when you look at the data, some of it's moving quickly, some not very quickly, like heating. All of them is a pretty slow thing. Other reactions can be much faster. So this here was the unit-wise technique of the detection techniques going through the units. And you can, as I mentioned earlier that it can be combined into an index later. That shows the data being sent through. Allows us to isolate faults within a unit, which is a useful bit of information. That wasn't necessarily the refinery's objective that we worked with, but it certainly was interesting. This one here, the hierarchy with dynamic PCA, slow feature analysis using different techniques, was much better. This here shows the t-squared, which is the, for all you who are familiar or not familiar, obviously this is the measured thing you can do with PCA. The other statistic is obviously the Q, which is the unmeasured value, which is also useful. We've done a lot of projects over the years and we use both. Here I just show the t-squared, and I believe that's all we use here in this study. Q gives you a measure of stuff that you didn't get included in the model, which is very useful because that may be what's driving the disturbance. But you can see here through the slow feature analysis, some of these, you can see both techniques, slow feature and fast feature. You can see here the line, the detection. 12 and 10 and 12 are not picked up with the slow feature. Both are, or the fast feature picks them up. So skipping the long lengthy analysis, including the wavelet presentations and all the rest that goes with that. Here's a summary of what we did. Time domain, frequency domain approaches, the unit-wise, the hierarchy PCA with slow feature analysis, the unit-wise wavelet, the hierarchy wavelet. These were the flares we looked at, 14. This is really here the column I'm most interested in. These are the ones where we absolutely could detect. Down here, the ones were possible detections. You could argue that this one was very good because it picked up 12. 4 of them were very fuzzy, but according to my original statement, the refinery would have been good with that. But these here, which is a little bit easier technique to use, you know, works quite well. And 11 to 14 is not too bad. A deep dive into the flares, not all of those 14 resulted in actual flares. The reason for that, of course, is plants have operators. Operators are very good and often they avert it themselves. But if, when we looked at the data, those were driving toward a flare. It could have been a false flare or a real flare. From an analytics point of view, it didn't matter. We see them as flares. An interesting sidebar, it's not in the presentation, but we had barely got the models developed. And I remember it was July 7th. It was just a few months after we had it working. The plant called us and they had a flare and they needed to analysis, and we ran it through. They immediately picked up the leading unit and equipment that drove the flare. It wasn't obvious to them looking at the data. That's why they asked us to do it. And we picked it off literally in minutes because it's on the data and it shows it, which thing caused it, how that happened. So that was a success. It's not here, but the second part of this study was also interesting in that it's not enough to just say I'm detecting a flare and throwing a note out for the operators. You had an independent flare. Obviously, their answer is this thing covers many square miles. What the hell are you talking about? What do I do? So can we at least give them a hint at what is leading us toward that? And so let's see, what data did I miss here? So we did spend some time in the plant. We looked at the flare gas recovery displays that they were using. We looked at how they were viewing the data. This is an interesting comment, nothing to do with the study, but when who's ever responsible that day for the flare gas recovery sees it coming, they would yell out that because everybody is responsible for reacting and who's flaring, and the operators would all collaborate quickly on who's flaring and why they're flaring. And then they would start taking action because they, in this case, they actually tied flares back to operator bonuses. So they had many considerable incentive to not flare. Anyway, we spent some time talking to the operators. We did what's called the task analysis. I'm sure many of you have done that when you've done display design or interaction work, but we did a study like that and picked off some things that were important to them. We designed a prototype, which I'm going to show you just how we did it. And I guess that's about it for here. So this is kind of what we started with. This is actually, for whatever it's worth, this is a fairly well done L1 display showing you the major units. Each box here represents an L2 display, and it's a summary of the L2s on the L1. All right, and obviously you operate from the L2s most of the time. Those are your control displays. That's what you normally see if you're walking in a control room. That's generally what's up, that's what they're looking at. And from there, if they have problems, they'll go to L3, which are debug. For a lot of you, that's common sense, but just pointing that out. So one of the things that we looked at was putting an indicator here on all the L1s. And you can see red means you're flaring. By that point, they kind of know it, but it puts it on the screen. Yellow means an impending flare. You've got 15 minutes. Obviously, up here at the top is where you normally are. Means nothing is shown. So that was the first thing. So then what do you do about it? So we went back to look at normal stuff that we've done for other analytics. And so what you can see here, because we have all 18 units and we have a considerable amount of information, we know which units are feeding the flare gas system. So we list them. Some of them were known about because flaring, generally what happens with units is that that is planned out, that they're going to do maintenance or something. And as you come down, you flare the gas. That's on the checklist. Everybody knows about it. This one, as you can see, snuck in. Wasn't planned for, and it is flaring. Depending on how close they are to the edge, you can simply drive you into that condition. So with this, who's ever in charge of the flare gas system would know immediately who's contributing, which operators are responsible, and what they should be doing. And with this kind of thing available, they're probably already acting on it to try and get it back down. They'll pull back production or whatever they have to do to avoid that impending flare condition. So that was a little bit of innovation. It may seem straightforward, but it wasn't until we looked at how they actually work together, and you got a bit of that in how I described it here. They work as a collaborative team to try and resolve that. You can see little messages here. I checked with the operator in charge of this unit to see what's going on. Why are they flaring? So conclusion. It's very much a kind of a general system to set up. We looked at both the time and frequency domain data. We picked 11 on this. It could have said 10 were absolutely, you have an impending flare, 1 is questionable. We looked at designing HMIs. And so that's it for my presentation. Again, I apologize for being a little bit late. I'm sure I finished easily on time. I moved through that probably too quickly. But I have questions. Actually, I finished on time for the presentation.
Yeah.
So we held it together.
You're good.
All right. So,
Let me know if I'm not accidentally saying this right, but to training the model, how much data in terms of like timeline use, like years of data?
that's a very good question. They gave us as much data as we wanted. So here, in this particular model that I'm showing, we had a year's worth of data. And so we just chopped out all the good data and used that as a training model. Obviously, standard statistical stuff, you do that and you take 60, 40%, whatever you want to do the training, and then there's testing. That's what we went with. So it was a very substantial amount of data. Very fortunate. They had a good PI system with the pull it out. Right.
So you mentioned, I mean, that it came up with 10, possibly another one, so 11 of the 14 flaring events. But you said they weren't actually flaring events. So how does that play into saying that it was a turning event?
When we looked at the data, they actually had 6 or 7, and we got all those. That wasn't listed there. There were some that were questionable, and we didn't know if they would have flared, but the operators took action. That's what I did. Okay. So from our point of view, we're outside the plan unless we went back and I'm sure the operators remember that you already have in the event data, right? Just take a look. We didn't do that. Good question. We have on other projects to follow with your question, we looked at heaters and column flooding and stuff. In those cases, we used about 3 years worth of data, trying to improve the models. And we had very good results there.
Specific processing of data were you looking at? Was it just flows contributing to flare patterns, each individual unit?
Yes.
Yeah.
With a little bit of caveat there. We couldn't have done this without the subject matter expert, control engineering, plant, and the operators. Part of that study that I talked about, they tell us which things